Okay, my name is Regis. I'll talk a little bit about today, bridging this mesoscale to the microscale and using that microscale data to inform SSRS using simplified engineering models to account for thermal and orographic updrafts. And our orographics, our updraft modeling efforts here at NREL has been divided into the orographic and thermal. And this is important because eagle flights are largely driven by the availability of vertical velocity because the birds want to use that to keep soaring. And oftentimes the community uses relatively simple models for updraft. And the thermal ones are usually constant in space, which is not very realistic. So our goal here at NREL is to really leverage all these years of microscale modeling capabilities that we developed, and we use turbulence resolving very high fidelity large eddy simulations of the atmospheric boundary layer of certain conditions of interest at the site of interest to help inform these models. So we use these very expensive simulations that require HPC, contains the terrain, resolves the turbulence, and we understand better what is going on in the atmosphere so we can inform these simpler models. And we leverage all the data available, for example, the wind toolkit that Carolina just talked about, and also the NOAA's high resolution rapid refresh data. I'll touch on that a little bit later. And on top of that, we also leverage some of the experimental campaigns that we have a wealth of data available. So jumping into the orographic updraft modeling, we base our work on the work of Brandis and Ombalski from several years ago, and they compute an orographic potential based on simple parameters, the slope and the difference between the wind direction aspect, and they use the horizontal wind speed. This model usually determines the correct sign of the updraft, but the magnitude is not really accurate. In fact, they use the horizontal wind speed, which, if you think of the boundary layer profile, increases with height. So our goal here is to really adjust this model, adjust the magnitude based on extra parameters that we can get from the geometry or the area of interest. The height above ground level, some measure of shelter and exposed index of whatever region you're trying to accomplish, and a measure of the terrain complexity. And we replace the varying horizontal wind speed height with a reference height, oftentimes at 80 meters or hub height, if you will. And we developed this model based on these LAS simulations of the atmosphere. So we started to develop with the height adjustment based on canonical simplified hill geometries under canonical neutral conditions, canonical unstable conditions. And then we moved on to realistic terrains like the top of the world in Wyoming, some Appalachian region in central Pennsylvania, and also executed under canonical conditions and diurnal cycles to further adjust the model. And to validate the model, we needed vertical velocity at high heights. And it turns out not a lot of experiments have that. Usually masses are relatively short, but we identified the Allies Mountain experiment, which is fairly recent, is of a few years ago. And they have a lot of data. The terrain is fairly complex. Here's a picture of the geometry, the surrounding geometry. And these are just some quotes from the paper, just indicating that this is it's a good case for us to use to compare our model. And first, let me show some comparisons with LES. And as I said, we executed on two terrains, Wyoming and the central PA. Wyoming is shown here on the left, the Appalachian region on the right. And at the bottom plot, you can see the terrain transect. These are transect over the whole region. And you can see the elevation map of the Wyoming and the elevation map of the Appalachian region. And if you pay attention to the scale, they're fairly different. And that is just two extremes to compare. In the top two plots, the first one is at 30 meters above ground level, and the middle one is at 80 meters above ground level. And looking at the Wyoming part first, the original model shown in blue kind of overestimates and underestimates as compared to the LES shown in black. And we are taking the LES here as the truth. And we adjust using all those corrections that I mentioned, and we get a fairly good match. And the same thing for 80 meters above ground level. And if you pay attention to the blue curve, it doesn't change a lot between the 30 and 80, and that's because there's no correction for height. And looking on the right plots, the Appalachian region, there's a lot of regions there, up to coordinate of 0 is not very steep. So the terrain is kind of similar to the Wyoming. And then we have the 300 meters high mountain. And you can see the updrafts goes up to 2.5 meters per second. And both models are comparable in that region. And I just want to point out the leeward side of the hill, it's been observed that we have positive updrafts there. And we do see that on the LS. And the models do not capture that. That's our current limitation we have. And now moving on, comparing with the LS experiment, and we focused on a single mast shown on these plots with the purple cross there. And we focused there because it's a good terrain area, it's a good region, and we have measurements. This is a reference mast that is 120 meters high. So we have vertical velocity available up to 120 meters, which makes a very good data set to compare. And this is some of the comparisons. And here, I know this plot is a little bit busy, but I'll walk you guys through it. I'm showing a span of 3 weeks. These are all 10-minute average data. At 40 meters, the 3 plots are 40 meters above ground level, 80 meters, and 120. The experiment data, the field data is in black, and the shaded area are the min-max. The darker shade is the 1 standard deviation. And the takeaway here is that the adjusted model shown in orange matches the trends a lot better than the blue curve, which is the original model. And you can see the blue one overestimates and underestimates at a lot of places, still within the min-max, but very far from the mean sometimes. And I want to point out, if you see here on 120, our adjusted is not perfect. It's not trying to be perfect, but it matches all these trends pretty well. So we were happy with that. We moved forward with the thermal updraft modeling, and that is quite challenging. Any atmosphere scientist will tell you that it's very difficult to predict where thermal will show up, the size, the shape, strength, how long it's going to live. So all of these things are, we decided to model, stochastically, and we base our work on, we separated thermal shape and thermal strength. And the shape we base on the work of Alan, which we have some shape functions that define what the thermal looks like at different heights. So our model is 3D, and depending on the height, it adjusts the magnitude and has some downdraft on the edges of the updraft. And this was a model developed for the autonomous soaring community, and it was nice that we could bring that into our model. And there are some additional modifications on top of that. The thermal strength we modified to follow the work of George Young. And also we imposed the restriction of the spacing between the thermals. That is 1.5 times the boundary layer height. In our parameters of the model, we have the locations, which are weighted by a function of the albedo and the convective velocity from the HER data set. And I'll talk about it in the next slide. The thermal strength is weighted by a function of the W star as well, the convective velocity, and the thermal size is weighted by a function of albedo. And we wrote such that our model can also be informed by field campaigns near the site of interest. I'm sorry, I have a typo there. I meant site of interest. And that can also adjust the magnitude of the thermals. And this is the HER data set, developed, made publicly available by NOAA, high resolution, rapid refresh, high resolution, 3 kilometers spatial resolution, rapid refresh, hourly, many variables available. This is just a sample here on the right of what is available. We have that integration built into SSRS. It's all there. It's on the dev branches if you guys want to try out later. And which brings me to a sample of what a thermal updraft field looks like. And on the left here, I plotted the albedo and convective velocity at that instant, so you can have an idea of what is guiding the realizations. The middle column is one realization, the right column is a second realization. And looking from far away on a 50 by 50 kilometers, they are very similar because they are driven by the same conditions. But if you zoom in, they're different, as they should. That's the nature of the model. And that brings me to our conclusions. So far, we developed some engineering models There are into SSRS. Again, this is on the dev branch if you want to try it out. Both models are 3D, which sets the stage for our 3D SSRS coming in the future. Our updraft model for the orographic better captures the magnitude as compared to the CFD data and experimental. In our limitations, we don't account for the separated flow on the leeward side of the hill, like I shown on that plot. And the thermal updraft still requires some tuning if you're going to a very different region.